hi everyone. As Paulo said, this is going to be the last talk, and then we're going to go into a panel. But before going to the panel, I would like to talk about the distributed web. So who am I? I'm David. I work at a company called Protocol Labs, and I'm a software engineer in peer-to-peer systems and also a researcher there. At Protocol Labs, we develop technologies, well, protocols, to make the web better. And as we have seen throughout the presentations today, the web has some issues. Things like identity, communications, interoperability play a huge deal in creating rich ecosystems that people can create their businesses on. However, we have seen growing in the last decade of like walled gardens, like these silos of information where people are just controlling users' information. And as Mark Andreessen put in 2011, like software is eating the world. And today, it's not even a question anymore if your business should be online. What that created was that like today, like every minute, like tons of data, like terabytes and terabytes of data are generated online. Video, news, images, messages, etc. And because the way that the internet was designed, it was designed to be dumb from the beginning, thanks to the end-to-end principle and some other architectural decisions, we keep passing the same bits in the wire over and over and over again. To illustrate this, let's look at a simple example. Like if I want to watch a video in a platform like YouTube, and imagining that we are 8 hops away from YouTube. We are actually more, I checked, we are like 14 hops from this venue. But like just to make it simple, let's consider 8. So like if we want like to watch a simple video, maybe around like 200 megabytes, like not a high res video, and we have like 30 machines here of people trying to download this video, we'll put like an effort of like 48 gigabytes of data passing through the wire, like hopping from YouTube to our user machines. But heck, like something is wrong with this picture, right? Like if the first user gets the data, and if they are in the same area as all the other users, why are we going to the backbone again? Like, why are we going to force the network to transfer the same bits over and over again? And these numbers get scary. For example, if we picked the video Gangnam Style, the screenshot that we see here, that was watched more than 2.5 billion times, it's like the most watched video in the history of YouTube, we have more than half of an exabyte of data passing in the wire. And probably a lot of these views are actually from the same machine, because I believe everyone has experience where like they are seeing a video in YouTube, Vimeo, or any other platform, and they click refresh in the browser, and suddenly it starts loading again. It starts downloading the whole thing again. We, like as engineers, as network engineers, as software engineers, try to solve this by putting CDNs in the middle, by putting like the content more close to the user, but this doesn't really solve the problem. It's just a simple patch. We still have the added delay of the number of hops that from our machines to where the CDNs are located. And telecoms are also have been trying to solve this problem with the added delay with like larger pipes. Like they are increasing the bandwidth that they deliver to users' homes. But unfortunately, even with all of that effort, like we don't see the bandwidth increasing as fast and as soon as we would expect. We can see like this is a projection or like data from 2007 to 2012. So just already like a little bit old, but we can see that the line and the average connection speed is pretty much flat, with the exception to Japan. Japan is a special case. And what we have seen also is that like as users generate more data and as storage gets cheaper, people will just like pass more and more data over the wire, which means like if the bandwidth is not increasing steadily and in a faster pace, and the data that's being produced is increasing really, really fast, the internet will just feel slow. Like if we could continue with the same behaviors, the same architectures, the internet will just start feeling slow, just because the data that we are transferring is like too large for the pipes that we have set up. And worse, even if we had like perfect connection, multiple gigabit fiber connection to every home, it doesn't solve every issue. We were promised like a decade ago by telecoms and like big software companies that everyone is going to get connected. Do not worry, like just build your app, your service on the web, and it's all going to be fine. But if we think like that's not the reality at all, like in cases where there's like low bandwidth, like if you are in a remote area or in a developing country, you just don't have like the connectivity that you are used to experience in a developing country. like something like interference, like more and more, there's more devices in the same room, sharing the same space, and there's a lot of interference in these radio signals that we use. There's congestion problems. There is also outage, like data center can go down. Like it has happened in the past, from fires to just like power being cut, like data centers can go down. And when that happens, it doesn't matter if you have a really nice fiber connection to your home, the service is just gone. And what we see is that all of these services that we use today, that we use to communicate with our loved ones, that we use to run our businesses, rely on the assumption that we are going to be always connected. And as soon as we disconnect from the backbone, gone. Like all of these things, like billions are lost in value every year. Each time there is like an outage of internet, a DDoS attack that just like targets a service, and then suddenly all the people that are using that service cannot use it for 2 days, and it's a huge loss. And not to speak about other problems that I could go in more depth, but like security is still a problem. We keep armoring the wire, putting HTTPS everywhere, but the truth is like the data is not encrypted at rest, so someone can just go there, change the data, and we cannot even tell. There is the really big problem of IoT. Like the web model, it doesn't work for IoT, so it's being kicked out of all of these devices, and people are building custom private protocols to develop their IoT solutions. There is a problem with permanence, like links keep being broken, we keep losing data, and also problems with censorship and control, where countries, governments can shut down the internet for an entire population just with like a kill switch. However, it's kind of ironic, because the web was meant to be distributed in the same way that the internet was designed to be distributed. ARPANET, the system that eventually evolved to the internet that we have today, was a communication platform to offer the US government and military to resist nuclear attacks. Like the whole design of the system was like if half of the country vanished, the other half could still work. Here we see like Robert Kahn like showing the first designs of the ARPANET, and he's explaining this store and forward technique, like this technique to transport data over all of these hubs, and like to enable the hubs to be smart enough to route the data through other paths if an outage happens. But over time, and although the web started as distributed, and it started shifting to a centralized architecture, which is kind of understandable. It's a way more model to reason about, like it's way more simple to understand, and there is like some opportunity costs and like, some social economic reasons and pressure that made it move to a centralized architecture. Nevertheless, the fact is that it doesn't have to be centralized at all. In fact, like we are destroying a lot of value or losing the ability to create a lot of value by it being so centralized. And we need to bring it back to become distributed so that we can take our services, our apps, our information to places where right now it is not possible. And it is with this frame in mind that I welcome you all to enter IPFS, the Interplanetary File System. IPFS is a content-addressed file system. It changes the model of the web from a fragile location base where a domain name resolves to an IP to a name resolving to an hash, to a content unique identifier. So what does this mean, changing the model? So in the traditional web through HTTP, you are looking for some resource, and then you do a domain name resolution, and you find the machine that's responsible for that resource, the central point of authority. You contact that machine, and you get the resource back. The problem is like when there is a network split, like when you lose connectivity to that machine, or even just like lose connectivity to the NS, and then you don't know which machine has the resource, right? And when this happens is when the web breaks. But with IPFS, it changes. Because we are requesting a content identifier, it doesn't matter who serves me the content. I just need to fetch it, ask the network who has the content, and then I can verify that I received the right content. And if there is a network split, it's OK. As long as the content lives on my side of the network, I'm totally fine. And even better, like if I already have the content myself, why should I go into the network in the first place? Like I can just like load it. It's kind of like beating the speed of light. You just like loads instantaneously. So IPFS, in essence, is a collection of great ideas from production-ready systems already deployed, and a lot of ideas that are present on the academia and distilled down together to create these better primitives for the web. Today, we have two implementations of this protocol that are developed, one in Go and one in JavaScript. The one in Go is for the users that are looking to build systems with IPFS and want to leverage the full system resources to maximize the data distribution. And the JavaScript implementation is focused on putting IPFS on the browser. Yeah, like it is possible. It is possible to run a fully distributed protocol on the browser without installing any plugins at all. And of course, this uses the peer-to-peer transport of the browser, WebRTC. So what is inside IPFS? Like starting from our self-describable data types. Like we use always self-describable data types to enable us to support several types of cryptographic hashes, several types of addresses, several types of encoding of data, like from Git blocks to Ethereum blocks to native IPFS data, any kind. And also, we pack our identifiers of the content more than just the hash value of the content itself, but also with a codec that describes what type of data that content is. Okay, I'll try to speed up. So this is like very useful for parsers and query engines because it like you basically bring up the extensions, the type of the file. And then like all of the data in IPFS is a secure data structure. Like everything is represented as a DAG and a cyclic graph, and every link is a Merkle link. A Merkle link means that like it's an like a secure link. You check it by its hash. The idea of like secure links, which we call Merkle links, comes from Ralph Merkle, the creator of the first Merkle tree. And you might be familiar with Merkle trees because you might have used them on Git. You might have used them on a blockchain, or even if you use software like BitTorrent or that, you are also using Merkleized data structures. And by the way, I need to make the note, like whoever said that money doesn't grow on trees didn't expect Bitcoin to come along. So intuitively, IPFS is this like Merkle forest where every Merkleized data structure can live and can be referenced to. Then we also have packed distributed naming. This is heavily inspired in a self-certified file system. It's basically naming that's like digitally signed, so it's a way more secure model than like just trusting some DNS point with some TTL value for those names. Then we have our network layer that grew up to become a standalone project that other groups are using called WePeer-to-Peer. WePeer-to-Peer is a secret sauce that enables us to do IPFS in the browser and also in desktops, native applications, because we can just change the properties of the network stack, keep the same primitives, the same addressing, and like the app that's running on top doesn't even have to know that it changed the runtime. So we get to hear a lot of developers saying that like IPFS is the layer that I always wanted as a developer, and it is the way that I always expected the web to work as a user. So what are people building with the distributed web? It seems like it's a great protocol for distributing video, like video and streaming, because like you can even put like more quality video on the network, and because everyone is going to be streaming this video, it's just going to load faster. Legal documents, people are using this because since you can authenticate every piece of data that you receive through IPFS, it is perfect for like documents that they have to be, they have some legal integrity. There is apps like IPFS Pics. You can go online today and like upload your photos, pictures of this event to IPFS Pics, and then not only have a shareable URL, you also have like the content hash, so that like even if IPFS Pics is online, you can still fetch these pictures. Apparently, 3D models and VR worlds are very big, so IPFS is like the perfect use case to transport those models. There's people building games, scientific data, like moving tons of terabytes of scientific research data. This is actually one of the main motivations that led to the development of IPFS. Blogs and websites, and totally distributed apps, and more, right? So we have started, like the conversation is still in the early beginning, but like we see a lot of interest of like do some cross-pollination between the Retring project and IPFS. And we think we can learn a lot from each other and reuse some parts and coalesce some of the efforts. For example, WePeer-to-Peer, the secret sauce that can give you the power to run in the browser or any kind of device, really, independent of the capabilities of the device. it's really modular. So you can like just pick the pieces that you want, the transport that you want, pack it into your application, and if there is some missing piece, you can always plug it in and like enrich the network stack with the features that you need. Another thing that's also very interesting is IPLD. So as we've seen, like Rethink levels leverages the JSON schema spec, and JSON schema is super useful because it gives context to the data. Like we can reason about the content, the data that we are passing through. The only serious issue with JSON schema is the fact that like it requires a URL. Like we can see at the top, there is a URL that like if we are not able to resolve this name, it means like this data has no validity at all. But with IPFS, you can like throw a schema ID, and then you can like not only cache the schemas more efficiently, you can also like retrieve them from your local peers, from your local network. So it enables Rethink to work in scenarios that it would not be possible before. You can see even the user got more happy. I'm sure if you got that. So really wrapping up. So IPFS, it is a protocol to upgrade the web. We don't want to create an alternative web. It's the way that the internet was built. Like we can change layers, and in the end, if the user, with adoption of IPFS, the user will just notice that he's using IPFS because the web will work in scenarios that it didn't work before and faster. So it's a protocol to make the web offline, to make the web smarter, distributed, permanent, safer, and especially faster. IPFS is a very large open source project. Like we have more than 350 contributors like coming, and 70 come every week from the academia, like doing research review, checking our specifications. We have people from the industry trying out our APIs and like deploying products. We have people that just come and contribute like with code. Like even our management, like our sprint management of the development is completely open, so anyone can just come and join the process. Everything is on GitHub and IRC. You can go to github.com/IPFS, and you will have access to all the code. Everything is MIT licensed. Again, everything is documented there. We work as a distributed team, so we write everything down. So yeah, this is what I have to share with you about IPFS today. I hope I managed to get you excited about IPFS as much as I am. Thank you again for inviting me. Excited to be part of the panel. So. Open for questions.
Great. So 1 or 2 questions before the panel.
Yeah. Okay. It says here I have 3 minutes.
Hi. I'm curious, how do you handle server-side dynamic content? Or use
server-side dynamic content? Does it have to be server-side?
Yeah, because I'm thinking most of the web nowadays, the web pages are generated dynamically at the server. So.
Okay, so even today, like there is a lot of pages that generated dynamic, but like there's also like this, like now there's a lot of pages being rendered at the client. So it can be really at any point in the, like it can be in any node on the network. But the way that we handle, well, let me just jump to the slide, which I didn't have a lot of time to explain, is this interplanetary naming system. So what this here is showing is that like instead of me pointing you to an hash of the content and like pointing you to a fixed point on the model of data, I point you to the hash of a public key. And that hash of the public key is resolvable in a system like a DHT. And you fetch the records that are digitally signed on this DHT, and they will have pointers to actual hashes of content. So me as a producer of content, like if I have my blog or my page, like a newsfeed or something, I can update the data model and then publish these records to the network. If you want something more faster than a DHT, so that like you want your feeds to look like real time, that's where like PubSub comes in. Like you can subscribe to feeds, authenticated feeds, and like when you receive an update on that feed, you always validate the digital signature, you validate that you are receiving an update from the provider that you trust, and then you just get the latest state, and then you fetch that hash, fetch that content from the network.
I was thinking more things along the side, like a shopping cart. Like if I go to Amazon and they have a shopping cart,
yeah,
it's dynamically generated for me by the server each time I reload the page, right? So you can have a mix of dynamic and mostly static content.
Okay, so in that model, what we see happening is like if you are serving your web page through HTTP, And if you have the data stored somewhere in a network, and if you have to always like mix and match something to serve to the user, what you have is IPFS on the server, and IPFS is the one fetching maybe assets for like, I know, pictures of the items that you're putting on the shopping cart. But in the end, you are building still like a very traditional like server-side application. You're just using IPFS maybe to make it more efficient to store the data in your data center or across data centers. The way to make that shopping cart distributed is like to move completely like that app into the like the front end, the client side, and have the client update the network itself as it touches the shopping cart, as it goes through the store. And you have like those two models. And there is like things, again, distributed authentication is really important because like you want to make sure that the user can tell the world, hey, I want to add this item and it's me. So like when I'm going to purchase, make sure like I just purchase the things that are from my cart. But yeah, so you can do both models. I think you would benefit more from rendering everything on the client side than on the server.
Thank you. One more question.
Hi. So I have actually two questions. First one is, do you think by your method, the IPFS, you mean to replicate the data to a series of hops? Because it's not concentrated in one server, but it's replicated to a lot of servers, let's say, distributed throughout the network. Are you planning to exchange communication, so to increase latency by just replicating data throughout the network instead of just pushing from one side on the server, of course?
So
this is the first question. Second question is, who is paying for all that storage? Because there is no centralized cloud provider. Who is holding that storage space, and of course it takes money to hold that data. Okay, so.
Awesome, thank you. Excellent questions. We do get that a lot. So IPFS is a protocol that works as a transport. So we don't force, contrary to other protocols that exist in this space that like force users to store data for other users, we are not forcing anyone to store anything. So in this case that we see here, like these other users will only have the data if they request it first themselves, so that they can like also reshare it with the rest of the network. What we are building on top of IPFS though, so like again, IPFS doesn't push data into anyone's machines without user's request. This is a really important part because we don't want people to be responsible for data that other people are like trying to store in the network. What we are building on top of IPFS is another protocol called Filecoin. And Filecoin is a cryptocurrency incentivized storage network where I'm able to pay to nodes that volunteer in the network. Think about like Amazon S3, but with a canonical way to contact nodes that offer storage in a network. I can say, I have these files, and I have this money, and I want to pay someone that offers to do the work of like storing these files for like a period of time for me. And then we have a proof of retrievability that we will check over time if the file is still like fetchable from the network. And for the nodes that are like serving that file over that period of time, we'll get compensated for storing the file for me. So this enables anyone with disks to plug it into the network and be part of this like economy where we can like pay to have lots of replicas. We can pay to have replicas in very fast points of the network. We can pay to have replicas in points of the network where it's very hard to like have data serving there. In remote areas, like again, developing countries, there is no data centers there, and the latencies are just huge. So we can pay to the users of like local remote places to store content so that when they request, the content is very close to them.